The first experiment is to find out if the half cell is a stable reference potential by measuring the electromotive force of the reaction between the saturated solution and the copper. This is the copper, this is the saturated solution. This lead completes the circuit to the meter, and we switch the meter on to voltages, DC voltages, and we found that it came immediately to 370, and it is now reducing. So you can watch the meter and you can see that it is not a stable potential because it's now gone down to 330. The meter determines the common input is 0. So the black terminal is 0 and the red lead is plugged into the red input, and this is conducting the electrical charges from the copper to the meter and going through the meter to create the measurement. Using a simple meter, we can see that a measurement, hang on a minute, let's change this over, switch this off, and we can see that the measurement is we can see that there's no measurement on it. Right. That's because I've got it set on the wrong one. Right. A. The measurement is now about 0.8 millivolts on this meter. Right. If I change these over on this meter, it goes to negative. So in other words, there is a charge, a potential, and it's going from positive to negative when I change the polarity here. So this in fact shows that there is in fact a charge in the relationship, the reaction between the copper and the saturated solution of copper sulfate. There is in fact an electromotive force is generated, is created. Now I'll plug this back in and you can see that this comes up at 370 straight away and it starts reducing. Alright, so you've seen that we are measuring the potential difference between this black lead and this red lead. The black lead is connected to the porous plug that would be connected to the ground, and this is connected to the traditional half cell connection. So the normal way of wiring this up is that the porous plug would be at the bottom and that would be stuck in the ground, and the copper rod would be in the saturated solution of copper sulfate. Right, anybody who's familiar with the DCVG and the CIPS and the standard way of measuring cathodic protection will be very familiar with this measurement. They will be very familiar with what is called a half cell. In this video I introduce the item that has been known as the half cell. This in fact is not a half cell. It is a piece of copper in a saturated solution of copper sulfate. The mistake was made because the Nernst equations refer to a half-cell reaction. That is the reaction that takes place at the interface between the electrolyte and the anode of a corrosion cell. This arrangement can be seen in DIN 50918. And somebody has just taken half of the laboratory setup, stuck it in the ground near a pipeline. This is utterly wrong and not supported by any science or scientist, and never has been. This next video is the first step in understanding the real science and how it must be applied to be credible. This is the arrangement that I made to compare anodes and cathodes on a strip of pipe. This is the method according to DIN 50918, where you have the copper in a saturated solution of copper sulfate and a Lugin capillary. These straws were filled with agar gel, which is a conductive gel but non-reactive, and I put these ends close to, right on the anode and the cathode respectively of corrosion cells that I created on a length of pipeline. This is the only scientific way of measuring corrosion reaction. DIN 50918. You'll now notice that this reading has reduced right the way down to 186. And if we leave it long enough, I have found that in fact it reverses. But a bit of a mystery is that it doesn't reverse on this meter when I change the inputs. So it must be something to do with the metering having a very, very high resistance, and the charges are not able to immediately react to the change in polarity on here. I don't know. The simple fact is that this proves that the half cell is not a stable reference potential. So the half cell itself, it's not a half cell, and it's not a stable reference potential. So that means that we're stuck, and we've got to find another way of measuring the corrosion reaction. And not only that, we've got to find a way of measuring the effects on that corrosion reaction of our cathodic protection systems. And it is for that purpose that I was forced to invent the Alexander cell, which is in fact a corrosion cell. And I will demonstrate that later in this series. At the present time, I am intent on demonstrating that the half cell cannot possibly be regarded as a stable reference potential. I've kept talking long enough, because if you're watching the readings on here, you will see that they have gone down to now 7 millivolts, and you will see that in fact they reverse. It's positive at the moment, and now it's gone negative. So you can see that the polarity of this reaction has changed. So there is some form of capacitance involved, and this reaction is not stable.